Hi everyone, it's me, Carolyn, and in this video we are going to be talking about the Poisson distribution. The Poisson distribution, similar to the binomial, does deal with discrete random variables. So it's just another one that's out there. There are others, and I will mention one at the end of this video. But we will not actually be covering it in our course. I just want you to be aware that there are others that do exist. But to get started, let's go to our guided notes and start looking at the Poisson. So the Poisson distribution, what it does is it's going to be looking at successes, very similar to successes in a binomial, but we're going to be looking at them over a specific interval. And that interval could be a time interval or a spatial interval. The two examples that I'll kind of touch on are, say you're at a drive-in window at a fast food joint, and between midnight and 1, we have an average number of cars or visitors of 3 per minute. And we'll talk about how that works. And also the other one that we'll see is the number of weeds in your garden is an average of 2 per square foot. And as we go through the definition, I'll kind of show you or talk to you about why those are Poisson situations. So the definition for a Poisson is given here. A random variable, again, we like to use capital letters to be random variables, so I chose the letter X, is going to be the number of successes in a fixed interval. It's going to follow this Poisson distribution or Poisson process if, first of all, the probability of 2 or more successes in a significantly small subinterval is 0. Now, looking at the two examples that I have above, if we subdivided our minute down to, say, millisecond, the probability of getting 2 visitors in a millisecond is basically 0. If I subdivided my square foot down to fractions of an inch, and if I have 2 per square foot, the fact that I'd get 2 in that teeny tiny area is basically, again, 0. The second qualification is that the probability of success is the same for any 2 intervals of the same length. So when I say 3 per minute, so if I'm talking 15 minutes, that rate doesn't change from one section to the next. And the same for the weeds in my garden. They're going to be evenly spaced 2 per square foot for the entire piece. And it's not like I have weed killer on one area and nothing on the other. So everything is very equal in likelihood. The third one is that the number of successes in any interval is independent of the number of successes in another subinterval or interval, provided they don't overlap, which makes sense. They don't want them to overlap. They would be dependent on each other. Basically, this is saying that what happens in the first 15 minutes from midnight to 1 is independent from the last 15 minutes or wherever that 15 minutes may lie. Same with my garden. If I'm looking at one area of the garden, it's going to be similar to another area of the garden, and they are independent from one another. One does not affect the other. And sometimes we do a lot of assumptions with that. Okay, the formula though then is as follows. If it does follow this Poisson, then the probability of getting X successes in that interval can be given by, now remembering X is the actual number of successes we're looking at, is equal to this lambda t. That's going to be raised to the X power divided by X factorial times e to this negative, and that's a lambda. And again, t, where X can take on any value, 0 to however large you want to go. This lambda that we have in here is going to be that average number of occurrences in an interval of length 1. So when we had 3 cars per minute, that would be a lambda. Our 2 weeds per square foot, that would be a lambda. It's kind of like a unit rate. If you were told that it's 17 flaws per 6 yards, you would want to reduce that down to something per 1 yard. The E that shows up in here is the E that we've seen with natural logs and things of that nature from high school, very similar to pi. It is just a number that shows up over and over and over again, and it is about 2.71828, and there is a button on our calculator that does that for us. Now, T that we have here is going to be the length of time that's in our questions. So if we're asking ourselves, how many visitors will we see in 20 minutes? How many weeds will I see in 5 square feet? So it's that area or that interval that we're looking at. Okay, I'm going to do an example here. And this one I'm going to do by hand. When I get to the next one, I will show us how to do it on Excel and StatCrunch as well. They are similar in nature again to the binomial when we did those using technology. So we'll get to that in a moment. But let's first of all, we'll go to our, suppose that we have an average of 3 cars per minute pulling into a drive-through at a local fast food restaurant. So like McDonald's or Wendy's or wherever. And we're going between the hours of midnight and 1. And we want to know, what is the probability that we have 18 cars show up between 12 and 12:15? Okay, so I'm going to kind of get my formula over here, and I'll write it down here so we have it. T of x is equal to x, and that's going to be my lambda t to the x, all divided by x factorial, e to the negative lambda t. Okay, so I'm just going to get all of our pieces here so that we can kind of put all of our things in, and then I'll show you on your calculator how we actually do this. So now in our example, we are looking for 18 cars. So that's my little x that we have. Our lambda is that rate that we are given in the problem. So our 3 cars per minute. So our lambda is 1. And lambda could be any value that you're looking for. Our t is going to be this from 12 to 12:15. Now we do have to be a little bit careful here because we want to make sure that our time and our intervals make sense to one another. So here we had 3 cars per minute. So our time that we're talking about is the minutes, okay? So we're going to have our t will then be this 15-minute time interval. All right, and now we're ready to put things into our formula. So we have this 3 times our 15, and we're going to be raising that to the 18th power. And then we're going to be dividing it by 18 factorial. And then we'll have this e to the negative 3 times 15. Okay, I am going to do a little bit of calculations before I actually go to the calculator. And the one calculation I will be doing is this 3 times 15. And 3 times 15 is 45. And that's just going to save me a little bit of time to calculate things in the calculator. So here we go. Okay. And I'm going to want to try to do this all in one line. We will notice if I did this in pieces and I try to take 45 to the 18th power, my calculator may blow up on me. In fact, it's going to be a very, very large number. So that's kind of why I want to do it all together. So here we go. So I'm going to do that 45, and I'm going to raise it to the 18th power. And that number is going to be divided by 18 factorial. So again, I have to remember where my factorial key is. That's in my PRB button over a couple. Oops. I have to go grab it. Okay, I've got that so far. I don't know if you guys can see that. There we go. There it is. Okay, I'm going to get that value because that's my ugly fraction. So you'll do notice it is very, very small. And we're going to then multiply this by e to that negative 14. So I'm going to go multiplication. And my E button, you'll notice mine here is going to be above this ln key. So it's this little function right there. So I need to do my second function, this, and you'll see the E pop up. And then I need to put in my negative 45. For me, my negative, I have to hit this key. And then I'm going to hit equals. And I get this tiny number. 1, 2, 3, 4, 5, 2, 5, 6. Okay, so 1, 2, 3, 4, 5, and then 2, 5, 6. So if you were looking at this probability, the chances that we only get 18 cars in that 15-minute interval is very unusual, less than 0.05. Okay, we might want to ask ourselves, how many cars do we expect to show up between midnight and 12:15 or in that 15-minute interval? So in other words, what is the mean? Again, this does not take statistical knowledge to figure this out. If we get 3 cars per minute and we're going for 15 minutes, we would just take that 3 times our 15. We should expect to see 45 cars, or 3 every minute steadily for that 15 minutes. And so that is our mean. And you notice I do have the formulas written down here for us. Our mean is that lambda times t. Notice it did show up in our formula here and here. And we also have, just for completion, if you wanted the standard deviation, you just take the square root of that. So for our problem, our standard deviation would be the square root of 45, which I'd have to do on my calculator. Square root 45. And we get 6.708. Okay. Again, I already noticed that this lambda times t was 45. We did have it show up twice in our piece. And a lot of times the technology we have does want that mean instead of the lambda separately and the t separately. They kind of want to know what was the average. So we usually rewrite that formula in this form. Okay, we're going to do one more example. And this one I will kind of do it 3 ways. I'll do it using our formula. And I will also do it using our technology just to kind of complete things out for us. We have my garden. It happens to be about 500 square feet. I think it is actually a little bit larger than that if you combine all of my gardens together. And let's suppose, for the sake of this example, that I have 2 weeds per square foot. There are some spots that are a little bit weedier than others, but for this problem, we'll just say there's 2 weeds per square foot. This type of thing is used when trying to measure plants and things like that. They will go into a area and they will map off and they'll kind of say, okay, this area looks like it's all about the same types of growth as far as plants go. And they will calculate how many are in that region, and then they will expand on that or extrapolate from that. So I've seen things done this way. Okay, and let's say in this problem, though, that I'm going to be looking at just a section of the garden that is 10 square feet. And I'm asking, what is the expected number of weeds in this area? So if we have 2 weeds per square foot and we're going for 10 square feet, our mean is that 2 times our 10, or 20. So we should see about 20 weeds in that 10 square foot area. Now, my next question then is, what is the probability that we get 25 weeds in that 10-foot area? And I'm going to use our new formula since we've already calculated the mean, and we're looking for 25. It's our mean raised to the x over x factorial times e to the negative mu, where our mean was that 20 to the 25th power divided by 25 factorial e to the negative 25th. And I can go and calculate this again on my calculator. I'm not going to actually show you the steps again, but I'm taking 20, raising it to the 25th power. And then I'm going to divide that by 25 factorial. And then I'm going to multiply that by e to the negative 25th. And I come up with 0.000300429 if I read all the digits on my calculator. Okay. We can use technology to do this for us. So if we're not real comfortable with pushing buttons on our calculators, we can get the technology to help us. And I'm going to go first into Excel. And very similar to the binomial, this Poisson is found in one of our functions. So we're going to insert a function. There we go. Making sure we are in the statistical category. And this is alphabetical, so I'm going to scroll down to the P's. And it's P-O, there it is, P-O-I-S-S-O-N distribution. Going to click OK. My X, that is the X that we're concerned about or asking the question about. We're looking for 25 weeds. Here you'll notice we do have the mean. So it doesn't ask for the lambda or the T, it asks for the mean. So that's why we want to calculate that expected number in that piece. Again, with this function, we can add from the bottom up. And here we only wanted it for one value, so I will put the word false on there. And I see we get 0.044. So what did I? Oh, my mistake. I found my mistake in my thing, so I will go back and show you. 0.04458 is our actual number. I make mistakes, and sometimes we can learn from those mistakes. But this 0.044 is actually correct. 44587 So we're going to go okay. I'm going to go back to sharing my guided notes and point out my error. I apologize for my error. My error is right here. It's our mean to the X and X, our E to the mean. So this should have been here a -20. Sorry about that. So I will fix mine and make sure I do get the correct answer. 20 to the 25th power. Divide that by 25 factorial. And now I'm making lots of mistakes. (20 factorial). And then multiply it by the E to the -20th power, not -25. And there's my 0.044. Shoot. Sorry about that. Again, I apologize for my error. Sometimes that's why I'm like, I like technology to help me, because sometimes humans, we make silly mistakes. And this is one of them. I stuck the wrong number in the wrong spot. Okay, so again, I'm going to go back into Excel. And actually, I'm just going to go into StatCrunch here. Okay. And show you how to do that in StatCrunch. So again, we do not need to type anything in StatCrunch, but we're going to go under Stats, our calculators, and it is alphabetical. So you'll notice Poisson is way down here towards the bottom. We do have options here as well. So, but again, it just asks for our mean, and our mean was that 20. And we are looking for the equal. The nice thing about StatCrunch versus Excel is we do have these options of inequalities versus equal to, and we are trying to find equal to 25. You'll notice that they does give us a nice picture, and you can see that nice looking bell happen. And again, if we had really large values, and there's some things we can do. We aren't going to go into it in this course. We can use that bell curve again to approximate some of our pieces. But you'll notice here I got that x equal to 25, and I get that 0.044588765. Again, technology is very quick to do a lot of the grunt work for us. So I recommend getting used to it. It's kind of like getting used to your calculator. So just play around with it and have some fun. I am going to stop sharing here and come back to me. Just to say that we did kind of finish chapter 6. And in our next videos, we'll be talking about chapter 7. I do want to mention that there is one other very well-known probability distribution for discrete random variables, and that is the exponential. And an exponential is a little different. It's very similar to the binomial, where you have two outcomes, a success and a failure. All of the trials are independent from one another. The probability does not change from one step to the next. The difference is we do not have a finite number of trials. So for example, shooting a basket until you make it, or rolling a die until you get a 6, flipping a coin until you get a head. And then the questions would be, what's the probability it took us 7 rolls to get that 6? What's the probability it took us 16 shots until we made it? Those would be the types of questions that they would be asking. But that is another probability distribution that we are just not going to have the time to cover. But if you took more statistics courses in your future, that would be one that would probably be looked at. In our next chapter, we're going to move away from the discrete situation and start looking at a continuous situation. But that is going to be in our next video. So if you do have any questions between now and then, please ask, and I will see you in the next videos.